Okay, let's get started. Hello and welcome everyone to Ethproofs call number 8. We have roughly 100 people on the call. People are still connecting. Today's topic is Poseidon, and this call is a little bit of an unscheduled call that was prompted by a research paper that was published about a month ago. And we actually had advance notice about this paper back in November, I believe, because the authors claimed a bounty on the Poseidon initiative that the Ethereum Foundation organizes, and they shared an early write-up of their ideas. And behind the scenes, we have been basically preparing for today and trying to come up with a reasonable strategy to move forward. So let me briefly share some slides, and then we'll get cracking with the presentations. So if you're new to these calls, we do have a Telegram group where these calls are announced, and you can register interest and get on the calendar invite. So yeah, I encourage you to join the Telegram group by scanning the QR code or entering ethproofs_community. So this is the agenda of the Ethproofs calls so far. And because hash functions are such an important topic, we're considering having a second call on hash functions, call 8b, that would be focused on alternatives to Poseidon. So there's interesting hash functions such as Blake that are being used today, for example, by Airbender. There's also SHA-256 that the Bitcoiners would probably want to use. And there's also newer hash functions like Monolith that have extremely good performance and are very, very promising, but need more eyes on them. And the theme of 2026 is security, and we'll have a whole series of talks on security topics, for example, formal verification, liveness, and fiat shimmer. So this is the paper that I was hinting at, which basically has shown that the attack surface on Poseidon 2 is materially different to the attack surface on Poseidon 1. The way that Poseidon 2 was framed is that it could potentially inherit the cryptanalysis of Poseidon 1. It's an extremely similar construction. It's by the same authors. It has an extremely similar name. But really, this new paper shows that these hash functions are materially different. And so in some sense, the lindiness, the amount of time resets. So previously, we wanted the assumption that Poseidon 2 had, in some sense, 7 years on lindiness, but now it just resets to 3 years because the paper is 3 years old. Now, from a performance standpoint, Poseidon 2 is extremely fast. It is quite a bit faster than Poseidon 1. And prior to this month, we were under the impression that Poseidon 2 was maybe 5 times more efficient than Poseidon 1, or potentially even more than 5 times more efficient. But what we've done in the last few weeks is optimize Poseidon 1 with novel optimizations that hadn't been implemented. And now we're at a point where actually Poseidon 1 is of similar performance to Poseidon 2, specifically less than 2 times slower. And this performance here is specifically referring to the plain text performance, not in-circuit performance. And when you look at an application like leanVM, which is this minimal zkWHIR for aggregating post-quantum signatures, the end-to-end slowdown is actually only 30% when moving from Poseidon 2 to Poseidon 1. And part of the reason is that doing all of these hashes is a subset of the overall workload. So there's some bad news, there's some good news. And basically what we're suggesting for lean consensus is to just do a switch from Poseidon 2 to Poseidon 1. Poseidon 2 is still not broken in the sense that with the current parameterization, the best known attacks still don't breach 128 bits of security. But Ethereum is extremely conservative on security, and we would want a hash function that has sufficient lindiness when it does launch on Ethereum. And we're planning to deploy this cryptography around 2029. Poseidon 1 is from 2019, so this would be a hash function that will have enjoyed 10 years of attention. And this is just a historical anecdote, but when SHA-2 was picked by Satoshi for Bitcoin, it was 8 years old. And when Vitalik picked Keccak for Ethereum, it was also 8 years old. So hopefully 10 years for Poseidon 1 should be sufficient. And one of the things that we'll be doing is focusing the $1 million Poseidon prize specifically on Poseidon 1 so that we can have as much confidence in it as possible. So we have these two initiatives that Dmitry will be talking about later in this call. We have a 2026 edition of the Poseidon initiative, which will be starting imminently with $150,000. And in addition to that, we will have $1 million for the Poseidon prize. And here it's specific to Poseidon 1, a total of $1.15 million. And this is a little bit of a stretch goal, but I'm hoping that we could start a NIST competition, similar to what we had with SHA-3 for these ZK friendly hashes. I think the world in general would greatly benefit from this, and it's kind of very coincidental. But Andrew, who's been at NIST for 18 years now, and who has been one of the key organizers of the SHA-3 competition, like he reached out to me just a few days ago, and I'm basically hoping to convince him to start such a competition maybe in 2028 or 2029. And if anyone here would like to help with this potential idea, then please get in touch. I think this would be really, really exciting, and to have some sort of a canonical NIST standardized ZK friendly hash function. Okay, so today's call is extremely packed. We're going to have a bunch of lightning talks, 2 minutes each, and then we're going to have 5 or actually maybe 6 presentations on Poseidon cryptanalysis, starting with the main event, which is the paper that I mentioned. So without further ado, let's start with the lightning presentations with Dan Boneh, who will give us an update on the proximity prize.
Yes, thanks, Justin. Good morning, everyone. So this is just a quick update on what's happening with the proximity prize. So as you know, the Ethereum Foundation set up this prize to study the proximity gaps, basically how which affects basically the length of hash-based proofs and other proofs. So the goal is basically to resolve the proximity conjecture. The Ethereum Foundation actually put some money into resolving this conjecture. And the question is, what are the rules of the prize? And so the judges are myself, Giacomo Fenzi, and Guy Larnon. We put together a paper that describes the goals of the prize, what is the problem that needs to be solved, what's the current state of knowledge. As you remember, I think in the last meeting, we had like a whole bunch of results on proximity gaps. I think we call it Proxtober or something like that. We had this explosion of results that happened. So we kind of put this all, relate them all to one another and kind of describe the state of the world. including even this new paper that was just posted yesterday, the Stu paper. We include that as well. It's supposed to be a living document that will continue to kind of state the state of the world and the goals of the prize. So the goal in one sentence is basically to resolve conjectures about mutual correlated agreement, line decoding, and list decoding. In one line, the grand challenges in the prize are stated as: given a code, can you identify the largest parameter delta, such that for any larger value than delta, these proximity gaps fail with a certain probability. And again, the paper specifies that very precisely. So the paper is done. People have reviewed it, and I hope we can post it on the Proximity Prize website probably within a few days. I'll leave it at that.
Perfect. Any questions for Dan?
Yeah, please work on it. It's beautiful problems.
Yes, and the whole space would benefit from it, not just Ethereum. Great, thank you, Dan. Next up, we have Mohsen, who will talk about Push Zero.
Hi, everyone. So I just want to bring to everyone's attention this tool that we have recently open sourced. Push Zero is a scheduling layer for zero-knowledge proof infrastructure. It's built upon a very simple architecture. It has queue, dispatcher, and collector. So basically, every piece is completely generic. You could replace it with your own tech stack. So the idea is any unit of work would be handled by the dispatcher. It could be a task in your prover, one of the sub-tasks that you have to prove. And the result is always published to the queue. And then you have this synchronization component that fetches all the results back together. And then you can continue your process on those. You can run parallel flows as much as you want. You can go completely parallel. You can have late synchronization with the power of the collectors. The collector itself is also a custom Rust trait. You can implement it the way you want. And the queue itself, what we call a message bus, is something that you can also replace. Right now, we are using NATS and Jetstream, but you can replace it with whatever queuing system that you want. So if I want to say some differentiating features of Push Zero, it has a guaranteed sub-proof collection, deadlock freeness, late synchronization. You could see from some particular workflows, this could give you a very significant boost. So we have seen that in practice. If your prover is written in Rust, you can use zero copy prover integration. So no duplicates, no serialization, no FFI. You can implement whatever redundancy, whatever pipeline you want to have. Fault recovery, chaos already tested, and complete linear scaling. It's already published, a preprint is published on Archive. It's been used in production for more than 14 million blocks for over a year. The source code is also fully open source. You can access it on GitHub. We have already tested it using ERE SDK for different backends. SP1 used in mainnet, on testnet, also verified with RISC-0 and Halo2, and any other prover you want. Some numbers, 5 per second overhead, and low latency. So if you want to talk about it, if you need any help with trying it out, reach out to me directly. Thanks very much for the time.
Thank you, Mohsen. Yeah, super exciting to see an open source orchestrator. And if you haven't spoken to Tal Lepton yet, he just recently joined the EF zkWHIR team. I think he's very much interested in this kind of stuff. So if I forget, please remind me to put you guys in touch. Dan Boneh in the chat, prompted by a question from Hector, basically is saying that the proximity prize paper should be posted on ePrint in the coming days, which is fantastic. Yeah, if you have any questions, feel free to ask them in the chat or to just unmute or raise your hand. Thank you, Mohsen. Next up, we have Justin Thaler, who will give us some Jolt updates.
All right. Hi, everyone. Look pretty blurry here, but hopefully you can hear me at least. All right, so I think I last gave a quick Jolt update back in late November. So just everything that's happened since then. So Jolt has integrated with ZeroOS, which means you can now compile Rust programs without needing any custom fork of Rust or need to manually stub syscalls and so forth. Jolt is now zero knowledge. It didn't really change any of the costs. No need for recursion or anything like that. And a GPU implementation is now complete. So the stuff that's well underway, which we'll be wrapping up in the coming weeks and months. So we're almost done with proof wrapping. It'll be an order of magnitude faster than sort of wrapping of alternative proofs, proof systems, because we can completely avoid non-native field arithmetic. So I'm particularly excited about getting down to 6 kilobyte size proofs, where you know, the extra prover time is a fraction of a second, right? But you can also go all the way down to like a gross 16 size proof, in a matter of multiple seconds, still much better than if you had non-native field arithmetic everywhere, like hashing-based systems need to do their wrappings. Jolt is generally targeted at proving big statements so far, although you can run Jolt on a phone. It's sort of unique in using only a few hundred bytes per cycle proved. So we have significant optimizations underway for the small statement sizes, the sort of thing that arises in most privacy-focused or client-side focused applications. And then finally, the big direction is switching from elliptic curve-based commitment schemes to lattices. And so we do expect major prover speedups when we do this, because we'll go from 256-bit fields to under 28-bit fields, proof size under 100 kilobytes, post-quantum security, and so forth. And of course, this will offer a major alternative to the hashing-based techniques that are the focus of today's call. So I think this will be a major transition for the space, and keep an eye on this. So that's my brief update on Jolt.
Amazing, thank you. And 1.6 billion cycles with 64 H1s, that's 25 megahertz per H1. And I believe the 5090 is actually more efficient than the H100s. So yeah, that's really excellent. I'm just wondering, do you have any kind of back of the envelope estimate on the speed up when moving to lattices?
Yeah, it's going to be at least, minimum 2x, but optimistically more like 4x. Yeah, so that's the back of the envelope, and then there's additional like completely orthogonal prover improvements that we have to get around to implementing. So hopefully, if the pure field switch is only good for 2x or 3x, there'll be another boost from just other stuff as well.
Okay, perfect. And on the GPU acceleration, I guess I have a couple of questions. One is, do you expect significant optimizations there because it's just such a recent implementation? And two, do you have a sense for when it might be open sourced?
Yeah, so for the first one, so I think the elliptic curve implementation that exists, yeah, it can probably get up to at least like 2.5 gigahertz on the same number of GPUs instead of 1.6. And then the hope is that as lattices come out, we get similar speedups on GPUs as the numbers I just mentioned, which is were for CPUs, but I think the GPU situation will be similar. So so moving well above 3 billion cycles per second on the same number of GPUs as the lattices come. The open source thing, we're doing everything we can, and so I don't really have something firm to say. But other than we look forward to it being open source very, very much. So it will be as soon as we possibly can figure it out.
Okay, perfect. And I guess, once you're running at 3 gigahertz, there's not much point in running faster because that's basically maxing out the sequential evaluator.
Exactly, yeah. So I mean, there is hope to, in certain settings, to parallelize the trace generation. But you're totally right. Like if you're running the trace generation serially, there's no point to going beyond 3 gigahertz of throughput because you just can't do the trace generation any faster than that. Yeah, that's just native execution speed. Yeah.
So we do have one question in the chat. Isan is asking, the previous announcement was regarding 64 5090s. This is for H100s.
Oh, I'm sorry. I just got it. You're right. 5090s. I just got it wrong. It was
Okay.
5090s. Yeah. Sorry. Yeah.
Okay, got it. Great update. Thank you so much, Justin. Next up, we have Federico, who will talk about lambdaVM.
Justin, I think I'll give the updates for Fede.
Okay, perfect.
So The basic design is almost finished. We have almost everything implemented. It's without recursion, it must be 25,000 lines of code. We need to add like some accelerators. We are currently changing some things of the design to make it way more efficient. So far, yeah, we got like several speed ups, and I hope we can have something nice to show during Fort mode and Beast mode days in Cannes. So hopefully I will be able to show you there some of the improvements we have been doing, and we have like several other ideas on how to improve, but development is going as planned. And then we hope to add recursion and some other cool tricks. So, and GPU should be on the way as soon as that part is finished.
Okay, excellent. And for those who don't know, this is an event, two events happening next week, one dedicated to post-quantum security, one dedicated to zkVMs, happening in Cannes at EthCC. Yeah, looking forward to the demo or the open sourcing or whatever the announcement is going to be. Thanks, Diego. Next up, we have Leo, who will talk about Venus.
Okay, let me share my screen. Can you see it?
Not yet.
Yes. How about now?
Yes.
Okay. Yeah. So here I'll introduce like the Venus, like which is like our graph-based zkVM backend. So the core idea is quite simple. So instead of like treating the proving as a backend function, we just encode the entire proving process as a computation graph. And this like shift unlock like three advantages. First of all, is of course the cross-kernel optimization. So when everything is represented as a graph, then we can optimize across like boundaries instead of being just stuck inside these isolated kernels. Yeah, which is quite critical for GPU efficiency. And second, like it make our life easier for security audits. So in the traditional HAL, which stands for hardware abstraction layer style designs, like which like we optimize kernel by kernels. So the important details such as like a fair Shamir or interactions or proof reduction are hidden inside the proof function. But with a graph, like everything is explicit. We can trace the proof obligation step by step, and even like build some independent checkers to verify the correctness. And the third one is the hardware support. A graph is directly complicable like to CUDA graph, like on almost like every GPU. And more importantly, to future hardware such as FPGA or ASIC. And this is what makes the architecture, the design, the future proof. The current status is that like we build our stuff based on Zisk, and we have finished the implementation of the CUDA implementation on Zisk version 0.15, and we demonstrate about 10% improvement over that. And yeah, since like right now, for like the next step is like we, of course, as you can see, like this 0.16 is out, like we are optimized for that. And hopefully we can also push further for FPGA or ASIC. We will open source the code after the upgrade is done. Yeah.
Yeah, super cool. I mean, there is another team that's also working on FPGA acceleration of Zisk, and the numbers that they shared with me was that it potentially like 4x more energy efficient than a 5090. And you know, one reason why this is exciting is that when you move from FPGA to ASIC, more or less you get a 10x improvement there on energy and efficiency. So we're potentially looking at a 40x improvement relative to the 5090s, which would be absolutely incredible because energy efficiency is the key bottleneck, at least for Ethereum scaling. Yeah, great to hear that you're also working on Zisk, and hopefully we have a sharing of ideas there.
Yeah, sure.
Great. And Mohsen, you have a question from Jonathan in the chat. Next up, oh, and the answer is yes. So basically, Jonathan was asking, is push0 agnostic from the underlying proof system? And he said, and yes. So this is potentially a new standard in the making where you can just focus on your proof system, and then all of the orchestration infrastructure can be handled by push0. Next up, we have Yoichi, who will present evm-asm.
Yes, evm-asm is about a guest. So the EVM that will run on the zkVMs. I'm sharing the slide. So the approach is to implement EVM directly using the RISC-V assembly. So not using any kind of compilers or higher level languages to produce RISC-V, just to write instructions like load, add, store, something like that. In the lean theorem prover, and prove theorems about these assembly programs that ultimately says that these instructions, sequences of instructions, implement the EVM. The big elephant in the room is that the Rust compiler has not been formally verified. So if you prove some nice properties about your Rust program, it doesn't translate automatically to the result of the compilation. So you have to do something else. And then the result of the compilation changes like every time the compiler changes or somebody comes up with a nice optimization or something. So you have to repeat this effort. Also, like defining C++ or Rust is not easy. It's complicated and sometimes takes like multiple stakeholders. So like takes years. The approach here is to vibe code the assembly program and vibe prove their properties in Lean. The nice thing is that the RISC-V specification itself has been translated into Lean already. The Ethereum Foundation gave some grants and many people worked on this. So I'm going to use this. And I'm also going to use the EVM specification in Lean. So I have the ingredients and the target both in Lean. Oh, time is up. Yeah, it's just in progress. Yes, I'm just trying the approach.
Yeah, I absolutely love this project. It's not one that we're currently supporting through the zkVM formal verification effort, but it's one that I think is extremely promising because you bypass all of the compiler. There's no Rust compiler. You just go directly to the metal, and this would have been a crazy project, even a year ago. But now it just seems, oh yeah, we can just do it, this might be the way forward to get to a canonical guest, which is end-to-end formally verified, and could potentially replace the current strategy that we have with client diversity. And I believe Yoichi, you will be coming to Cannes, so really looking forward to the discussions.
Yes, see you there.
Nice. Next up, we have Emile, who will talk about Phanse aggregation.
Hi, I will just simply share my screen and show you an example of hash-based signatures aggregation with a hash-based snark. So as you can see, there is like 1040 XMSS being aggregated 3 times, and then you recursively aggregate those 3 aggregated signatures, and you continue and so on. And in the end, you end up with the total aggregation below 128 kilobytes without proximity gap conjectures. And you can be even lower, like approximately 75 kilobytes with those conjectures. And everything has based post-quantum, etc. That's it for me. Thanks.
Yeah, that's super, super cool. And did I see correctly on the screenshot that not only are you merging aggregate signatures, but you're also removing signatures?
Yes, it's because we allow the intersection to be non-empty. So basically, when the intersection is 5, I've written -5, meaning that the total number of aggregated signatures is 5 times less than the sum of the 2 previously aggregated signatures.
Nice. And would it be possible?
I didn't quite have time to see the slide.
Okay,
Can you post a link to it?
I will share it again. Sorry. Okay. Yes.
Cool.
Yeah, and in an Ethereum context, this would all be happening in parallel across different subnets, and so what took a few seconds here will hopefully take a fractions of a second. Super cool. Thank you so much, Emile. Cool. Next up, we have Guy, who will talk about the first approach to adding zk to hash-based NOCs. Guy, the floor is yours.
Yeah. Okay, so hey everyone. So I'll tell you about our work on zero-knowledge IOPPs for constrained elite codes. So let me start with a bit of background. So what we want is the best proximity test. And so far, most of the efforts were towards minimizing the query complexity, which translates to the argument size for hash-based NOCs. Now, we might also like to have faster provers, and most significantly for us, honest verifier zero-knowledge. So the codes we consider in this work are interleaved codes, which is a rather general family of codes that is generated by stacking code words from a base code to form a matrix, and the alphabet of this code are the columns of this matrix. And prior works for IOPPs for this type of codes achieved different things like with these three dimensions. So in terms of soundness, what we would like to have is list decoding soundness, which reduces the number of queries. In terms of code, we would like to have code agnostic construction that we can instantiate with whatever code we want. In terms of zero knowledge, we would like to achieve that, and we would like to have as little overhead as possible. And the question that we ask is, can we get all of the above simultaneously? And the answer is yes. We can say that the state-of-the-art zero-knowledge IOPPs are as efficient as non-zero knowledge state-of-the-art IOPPs, where the zero knowledge cost manifests in the lower order terms. So in terms of techniques, I'll just tell you very briefly that what we do is that we avoid the naive full masking approach, which incurs like an overhead of at least 2. And what we do instead is that we use like mask of sublinear size, and this allows us to get basically no efficiency loss. Now, this is easier said than done because of the size mismatches between the big code word and the smaller mask, and we use a new committed soundtrack relation to propagate these claims. And in terms of other goodies, we also recover previous protocols using unified framework, and we have a modular construction that we can instantiate. Modular construction with zero-knowledge building blocks and composition. And finally, we rely heavily on zero-knowledge codes and distance. And we also discuss the benefits of distance amplified codes in terms of efficiency. So that's from me.
Wow, super cool. And in the Ethereum context, we've already started work on shielded transfers at the L1, so equivalent functionality to Zcash on Ethereum L1. And we want to make lean-VM zk true zk, perfect timing. And I believe also that Zcash might also be interested in post-quantum zk as well. And yes. Coincidentally, we have thank you, Dara. We have another approach, which was, I guess, made public today from Ron. So Ron, I'll let you explain your Veil approach.
Thanks. Yeah, can you see my screen?
Yes.
Perfect. Hi, everyone. So happy to tell you about this new work, Veil, which we just published on, which is a very kind of simple and lightweight way to add zero knowledge to hash-based multilinear proof systems. So first of all, what are typical approaches for adding ZK? So one thing that is very typically done already since the 80s is adding ZK via proof recursion or composition. So composing a non-ZK proof system with a ZK proof system. That's a very typical approach. Another one is more in the lines of what Guy just described, which is kind of adding ZK from the ground up to each and every component in the system, and to also kind of all the glue between the components. So these are two kind of typical approaches. They both have pros and cons. So the composition approach is very modular. It's very clean. You just sort of wrap everything at the end and you're happy. But it is costly because the ZK proof system is now proving kind of an expensive verification that usually involves a lot of Merkle hashes and it turns out to be quite expensive, you also kind of have to wait for the non-ZK proof system to finish before starting to prove in ZK. That's the disadvantage. For sort of the ground up approach, the main disadvantage is that it's sort of very intrusive to the code base. You have to change all of your components to support ZK, which kind of can be quite hairy, hard to maintain and audit. And what we were wondering is, can you get the best of both worlds? That's what we were attempting to get with Veil. So Veil is a very simple and lightweight compiler. It kind of tries to follow the composition approach, but without the caveats. And it's very much inspired by Matteo and Abi's work on anonymous credentials that's implemented in Google Wallet. So we implemented this as sort of a POC. What I'm reporting here is for kind of a very simple inner product computation. So you commit to two vectors and prove their inner product. What we're seeing is sort of very small overheads. If you were to add this to a complex system like SP1, the overheads would be much smaller because you only do it at the end. It's a lightning talk. I won't have time at all to tell you about how it's done, but happy to chat about it afterwards. And the paper is online, as is the implementation.
Oh, very cool. I didn't realize the paper was also online. I guess I'm curious, for the previous presentation, Guy, is there any overhead to the proof size as well?
Yeah, I mean, there is going to be a small overhead coming from the mask that you need to send, but it's going to be a little order of 1 compared to the big code word that you send initially. So it will be like something, you can imagine something like the code word being of size n and the masks of being of size like log n or like square root n. So like it's n times 1 plus eta of 1. Okay, and concretely, do you think you'll be roughly similar to the 12%? Yeah, I'm not sure about that, but I think we are trying to get some estimate of how it will perform in practice. Yeah.
Yeah, and one thing worth saying is that within a complex system in which you do sharding, you can also like compose a ZK proof with a non-ZK proof to shrink the size of the proof, if that's what you're worried about. Right.
Makes sense. Got it. Thank you, Ron. Next up, we have Fara and Will, who will give Ethproofs updates.
Share my screen. Okay, yeah, we had another kind of major update to Ethproofs. The real-time proving cohort is live and running every Sunday night. It's capturing a snapshot of the last 7 days. And just as a reminder, to be eligible for the cohort, a prover must be using a zkVM that has been integrated into SoundCloud, because that's security sprint milestone 1. You have to be running a 1-to-1 multi-GPU cluster, so trying to submit for every block. You have to have a performance score right now of at least 70%, so that's sub 10-second blocks 70% of the time. And you have to have a liveness score of at least 95%.
Sorry about this.
That's all right. And so also we have improved metrics and charts on every page too. So definitely go check it out and give us feedback on anything you see there that you have questions about. And then our next chunk of work that we have coming up is we're going to try to improve our block timestamp by running our own nodes. We have that kind of underway. The zk attester validator client is actually in the staking queue, so we can kind of monitor that performance and begin working on that again and trying to surface that information on Ethproofs itself. And then we will also be integrating into Ethproofs this 1 in 10 kind of proving cluster that Will is going to talk about next, which is this on-prem proving cluster.
Thanks. Yeah, so in addition to the pushes to the platform that went up earlier this week, we also announced both a new, I guess, grant initiative, this on-prem proving initiative, and it gives us an opportunity to like really take a close look at the ground rules for the existing grants that remained unclaimed from last year, the real-time proving grants. So if you go to ethproofs.org/blog, there's a post that talks through both of those programs. the TLDR with the on-prem is that, we really want to do what we can as Ethproofs to emphasize and encourage on-prem proving. And so with our available grant funds, we approached the 5 teams that participated in the real-time proving cohort, and 4 of them have decided that they're going to receive the grants. And so through that, they're going to get to enough funding to procure some hardware that's going to allow them to be able to kind of stand up and do these 1 in 10 proving cohorts. And so we're hoping to sort of use this to monitor all the different nuances and individual behaviors of distributed on-prem proving, and hopefully continue to grow that cohort after we kind of roll out this initial round. And then also in that same blog post, you'll see a lot of information about the real-time proving. Just a quick note that, please don't conflate these grants or any competitions with the work that the zkWHM team is doing. That's its own separate evaluation process for the actual L1 zkWHM. And then if you go forward to the next slide, just a quick reminder that we've got Beast Mode coming up next Saturday in Cannes. Very excited. A lot of great content coming together. You can find more online or DM me.
Perfect. Super exciting. And yeah, as you can probably tell, the EF is trying to support many different initiatives financially. We have the formal verification, we have the Poseidon Prize, we have the Proximity Prize, we're paying for hardware. And I think as we move closer and closer to production and the path forward is more and more clear, we're going to be doubling down, tripling down in terms of financial support to actually get this on mainnet. Cool. This is going to be a long call. I think we're going to overrun the 2 hours by a little bit. But now we have the main event, which is the paper that triggered this unscheduled call. We're going to have Àlex present his skipping class paper.
Hello, everyone. Can you see the screen?
Yes.
Okay. So my name is Àlex, and this is the presentation about the skipping class paper. Thank you very much for the introduction, Justin. And this is a joint work with Simon, a very great postdoc researcher at ETH Zurich. Now, in this presentation, I'll be talking about the Poseidon's structure and what are we exactly exploiting. Next, I'm going to define what is an algebraic attack and what has been done before. Then I'm going to exemplify our contributions by explaining how we broke this bounty instance in the Poseidon initiative. Next, I'll talk about what are our contributions beyond the bounty. And finally, I will summarize the presentation and let the turn for the questions. So first, this is the Poseidon 2 design. As you can see, we have a permutation over T-field elements that can be used either in sponge or compression mode, giving rise to the hash function. And this permutation consists on a series of matrix multiplications.
Àlex, your slides are not updating for some reason. We're still seeing the title slide.
Oh. What? Sorry. Can you?
No worries.
Are now updated?
Now we can see kind of the toolbar. Just
sorry.
A very small subset of your screen.
Okay. What about now?
That's better. Yes.
Okay.
Thank you.
Okay. Thanks. Okay. So, as I was saying, the Poseidon is a permutation over T-field elements that can be used either in sponge or compression mode. And this permutation takes as an input T-field elements and applies matrix multiplications, constant additions, and element-wise power maps. In this structure, the difference between Poseidon and Poseidon 2, among others, is the choice of the matrix multiplication, which will be important for our contributions, and we will detail later. But the important information for now is that we are only applying sums and multiplications so that the output can be expressed as some polynomial on the input variables, which in particular gives rise to what we call an algebraic attack. Now, the problem that is used to benchmark different algebraic attacks is called the constraint input, constraint output problem, which statement is as follows. We want to find a certain input such that the last k components, remember we're talking about k field elements, so it's not k bits, but k field elements that are equal to 0. And the output of the permutation should have as well k output elements being equal to 0. Now, how can we model this problem algebraically? As I said before, the permutation consists of several sums and products of the input. So if we model the input as certain variables and then propagate those variables through the permutation, in this example, T is 8 and K is 3, the last 3 output components will be certain polynomials on the inputs. Now, finding a solution to the constraint input, constraint output problem consists of finding a solution to this system of equations. So 2 observations here. For most parameters of Poseidon, the number of variables is greater than the number of equations. Here we have 5 variables and 3 equations. So this is an overdetermined system. A possible way of reducing the number of variables could be evaluating x3 and x4 to 0 and then solving a system of 3 equations in 3 variables. Now notice that those polynomials, as they arise from the Poseidon permutation, in the Poseidon permutation we are applying a power map x to the alpha at every round. So in every round, the degree of the polynomials are increased by a factor of alpha. And if Poseidon consists on rounds, the output of the permutation will be of degree alpha to the r, where alpha is usually 3, 5, or 7, a small integer. Now, intuitively, higher degrees make the system harder. So instead of evaluating x3 and x4 equal to 0, what we can do is finding a smarter algebraic technique to reduce the degree of those polynomials and then making the system easier. Now, this has been done first, at least in the Poseidon permutation back in 2022. The idea of the round skipping trick is as follows. We decompose the permutation as 2 smaller permutations, pi1 and pi2, where usually pi1 consists on the first 1 or 2 rounds, and pi2 is the next, all the remaining rounds of Poseidon. The idea is finding a certain parameterization, which is depicted as bi's. So b0 could be, for example, x0 plus x1 plus x2. And for every equation that you can see in the middle, if we evaluate at a certain value, at a certain x0, x1, x2, this parameterization has the property that the inverse under pi1 will always be a valid input. So in this example, that means that the last 3 input components will be equal to 0. Now, how can this be used for an attack? Well, given this parameterization, we can just forward it through the pi2 permutation, which consists on several Poseidon rounds. Then we will obtain 3 polynomials, and we can solve a system that consists of equaling those polynomials to 0. In particular, the advantage comes from the degree of this parameterization. If the degree is smaller than the one that we would obtain if we directly forward those variables from the input, then the problem will become easier. Now, this is a very abstract idea, so let me exemplify this with our attack. Now, in this section, I'm going to be talking about how we broke the biggest bounty instance in the Ethereum Poseidon initiative. This concrete instance has 16 input elements. These elements are over a prime field of where the prime is the M31 Mersenne prime. And the last two inputs and last two outputs are constrained to 0. Also, the power map is 5, and the permutation consists on 10 rounds in total, which means that if we propagate the input variables through the whole permutation, we are raising to the power of 5 10 times, which means that the output polynomial will be of degree 5 to the 10. Now, as Justin said at the beginning of this call, what we are doing is exploiting a certain structure that is present in Poseidon 2, but is not present in Poseidon, which in particular is, as I said in the beginning of this presentation, the external layer. So let's take a look at how this external layer looks like. In Poseidon, the linear layer was an MDS matrix, while in Poseidon 2, the external layer is, as given in this slide. These are two equivalent definitions, where the second definition is a 16 by 16 matrix given in blocks of 4 times 4 matrices, where this M is the matrix that we can see at the right, 5, 7, 1, 3, etc. Now, in particular, the structure that we are exploiting is that the left matrix of this tensor product has this eigenvector 0, 1, minus 1, 0. Let me explain how with an example. Suppose that the input of our permutation, remember it has 16 elements, is of the following form, where every letter consists of a vector of 4 elements. So we have 4 elements plus 4 elements plus 4 elements plus 4 elements, 16 in total. And because we are trying to find a zkWHIR solution, the last two input elements are forced to be 0. That means that we have 14 degrees of freedom in total that can be exploited. These 14 degrees of freedom are used as follows. 4 degrees of freedom are the variables in X, and the other 10 degrees of freedom are used to define certain constants that I haven't specified yet, which are U0, U1, and U3. U0, U1 are vectors of 4 constants. U3 is a vector of 2 constants and 2 zeros. Now, if you propagate this input state, which I just defined through the first external layer, you will obtain something as can be seen on the right. In particular, neither the 4 first components nor the 4 last components depend on the variables. If we take a closer look at the second component, we have something of the form mx plus a certain constant to the power of 5. And in the third component, we have minus mx plus a certain constant to the power of 5. What we are going to impose now is that those constants have a certain relation. In particular, if I define y to be a vector of variables equal to the second component, that is mx plus certain constant to the power of 5, I want the third component to be minus mx minus the exact same constant to the power of 5. If this happens, then the third component will be minus y. So what is the advantage here? We had an input of certain variables, and after the first round, we will obtain polynomials of degree 5 in those variables. If we can make this change of variables, then our parameterization is of degree 1. And decreasing the degree means making the final system easier. Now, this structure can be iterated again. So if this is the input at the second external layer, after applying this layer, we can again impose these similar equations and make another change of variables. So after 2 rounds, we have another parameterization of degree 1 instead of a parameterization of degree 25, which will make the system way easier. Now, we could keep iterating this. We could even skip some partial rounds, but in this presentation, I will leave it just here, and I refer to the details at the Appendix B of our paper. Now, just to summarize, what I'm saying is we are defining certain equations so that the round skip exists. Then we want to find these certain solutions. We want to find what are those UIs at the input. And once we find those constants, then we can make the change of variables that will give us a round skip. In our case, we brute force one variable. So our contribution can be summarized as follows. We're basically saying that to find a solution to a system, we do some round skips, and then we find a solution to the system. Okay, let's look at the experimental results. Basically, because we're lowering the degree of the equations a lot, in this particular bounty instance, the speedup expected is of around 18.5 bits. We're going to give more details in the appendix B of the paper. Now, let's talk about our other contributions and key takeaways of our results. First of all, the round skips consist of defining certain, using the degrees of freedom of the input to skip rounds. In particular, we are using 4 degrees of freedom to skip every round. That means that intuitively, the larger the amount of degrees of freedom at the input, the more rounds that we can skip. So the round skip doesn't work exactly the same for different parameter sets. Intuitively, the larger the state size, the more degrees of freedom, so the more rounds that we can skip. And the larger the number of constraints, the less degrees of freedom, because we will have more zeros, so the less rounds that we will be able to skip. So in our paper, we detail a general round skip strategy for a variety of parameters, in particular, parameters suggested by the authors. As I said before, we also show weakness in the internal layer, which was used to break this bounty instance, but also to describe the most powerful attack against full run Poseidon. We also exploit the mode of operation of our permutation. So I said at the beginning that Poseidon can be used either in sponge mode or compression mode. And in the next slide, I'm going to give some intuition on why the sponge mode of operation can be easier than solving the constraint input, constraint output problem, which is a problem used to benchmark these algebraic attacks. Also, we describe novel modeling for the collision attack that also improves upon the SICO problem, which I'm going to explain in 2 slides. And finally, we adapt previous Gröbner cryptanalysis to the case where we can do some run skips to the permutation, just to argue what are the security margins of Poseidon and why our attack does not threaten the 128 bits of security of what they claim in some instances. Also, we explore possible mitigations. So as Justin said at the beginning, we are exploiting something that is in Poseidon 2 that it's not in Poseidon. That is the external layer that I've described previously. So a very natural question is, well, do we need an MDS matrix to mitigate that attack that is going back to Poseidon? Well, the surprising answer is that there exists a matrix that is as efficient as the matrix in Poseidon 2, but is completely immune to the attacks described in this paper. Okay. Now let's give an intuition of the round skips in sponge mode. Now let me remind you how the sponge mode works. This picture is an example of 2 absorbing phases and 1 squeezing phases. In this case, we have 2 messages. A message that has 2 parts, M0 and M1. Then there is an initial value, which I set to be 0 for simplicity. And then we're adding the message in the rate part of the state. We propagate this input state through the first permutation. At the output, we add element-wise the second part of the message, and then we apply the permutation to obtain the hash. So what's the intuitive idea here? The difference between sponge mode and the constraint input, constraint output problem is that in the second permutation, we have several variables at the input as before, but the lower entries of the permutation, A5, A6, A7 in the example, are not constants fixed by the designer, which were previously 0, but are constants given by the previous permutation. So the intuitive idea is that we can use degrees of freedom of the input of the previous permutation to choose an appropriate lower elements such that we gain certain degrees of freedom for the second permutation. And as I said before, the more degrees of freedom, the easier it is to skip rounds. Let's go to the collision attack intuition. In the pre-image attack, we have as many polynomials as the size of the hash. And each polynomial has as many variables as the size of the hash. So in the example, we will have to parameterize a 4-dimensional variety because we have 4 equations. However, in the collision attack, we can parameterize only a 2-dimensional variety twice, and then we have 4 variables as well, and 4 variables and 4 equations is as well defined. So what's the tricky part here? In the pre-image attack, we need to parameterize a 4-dimensional variety, in the collision a 2-dimensional variety, and in some cases, parameterizing a lower dimensional variety is easier than a higher dimensional variety, which basically means that we can skip more rounds in the collision attack. Now, this is a summary of the speedups that we obtain in our paper. What can be seen in this table is that the speedups obtained in the zkWHIR problem are smaller than the ones obtained either in the pre-image attack in compression or sponge, and the greatest speedup obtained is in the collision attack. Here, this table, the normal values of alpha is 3, 5, 7, and omega is the linear algebra constant, which can be chosen to be 2 as a lower bound for the speedup. So for example, in the pre-image attack for sponge mode in the koala bear example, which is this alpha to the 11 omega, the speedup will be something like 3 to the 22. Just to summarize this presentation, we have revisited algebraic attacks against Poseidon. We have explained the constraint input and constraint output hardness. And then I've explained what's the exact weakness that we're exploiting in the linear layer, how the attacks can get better in the sponge mode and in the collision attack. Thanks for your attention. And if you want to read further details, here's the paper.
Amazing. Thank you, Àlex. If you have any questions, feel free to raise your hand or ask in the chat or unmute. We do have one question in the chat from Dara, who was asking about jive mode, 2-to-1 compression, as opposed, I guess, to
it's originally described in the NMY paper, but I think it would also apply to Poseidon.
Yeah, the 2-to-1 compression is we have less degrees of freedom, so the roundscape is worse. And well, in my presentation, I simplified the table to only 3-to-1 compressions. But in the paper, you can see, like in the initial table, I'd say it's page 2 or 3. We give precise roundscapes for the 2-to-1 compression as well. Yeah.
So is that 2-to-1 compression using sponge or using jive?
No. Using sponge, we don't have any roundscape for 2-to-1.
All right. Okay. Thanks.
Jive with the identity matrix. Yeah.
Àlex, do you think there's more juice to squeeze on the attacks? Of course, they can only get better. And what is your confidence level on Poseidon 2? Do you think it will break at some point?
What a question. Yeah. I think in the roundscape part, it's hard to get it better. But I think in the solving part, there are potential improvements. There's still some Gröbner basic exploratory I think. So I think it's hard to predict. The Poseidon designers took a very large security margin, so it's hard to get it lower than 128 bits of security. But I think we would need more time to investigate.
Thank you anyway, because we were considering using Poseidon 2 in Zcash, and now we will not. I mean, partly the performance issue that you raised at the start, Justin, influences that as well.
Yeah, so just to remark something, our attack does not apply to all particular parameters. In particular, there are parameters for Poseidon 2 for which our attack does not improve the previous state of the art. So for example, if the state size is 4 or 8, we have no improvement. And yeah, in this case, compression.
I think also for large enough fields, the attack could be too expensive. Is that right?
Probably it's more related to the state size, but I'd say it's correlated, no?
Okay.
Àlex, you mentioned in passing that we could find MDS matrices that are just as efficient than the Poseidon 2 matrix. Is that did I understand that correctly?
I didn't say MDS matrices. I said matrices that are resistant to our attack and that are as efficient as the Poseidon 2 matrices.
I see, but they're not MDS.
The ones that we have found, no.
Okay, got it.
So it was just to better understand the scope of our attack, not to propose a new matrix, of course.
Okay, understood. And have you spent any time looking at Poseidon 1 as well?
Yes, but only after the publication of the skipping class.
Okay, got it.
So not much time, yeah.
Okay, and is it fair to say that none of the attacks that have been published apply to Poseidon 1?
In our paper.
In your paper, yes.
Yeah, exactly, yes.
What's your intuition about the security of Poseidon 1.1? I know that's a very general question.
Yeah, my intuition is, I mean, it's hard to say. This is not mathematical and we don't have any proof. This is just an intuition and I can be wrong, but I think Poseidon 1 or 2 are more secure for larger parameters, for larger prim sizes and smaller state sizes. Basically because it's more studied. So I think the best understanding of the Gröbner basis attack has only come less than half a year ago, and there can be improvements. So yeah, I think the smaller state size hasn't been as studied as the larger field size. Okay.
And one side note on these like small primes, the Poseidon prize, the $1 million, will be dedicated to small primes. So yeah, you're right. Like in practice, in the past, Poseidon 1 was instantiated with these larger primes. Great. Any further questions from the audience? If not, thank you so much, Àlex. Fantastic work and great presentation. And looking forward to your future work, potentially on Poseidon 1. That sounds exciting.
Thanks to you and thanks for your introduction.
Next up, we have Katharina, who will talk about Gröbner basis.
Yes, hi. Can you see my slides?
Yes.
Great. In a second. Good. Yeah. So this talk will just be a very quick overview of Gröbner basis cryptanalysis of Poseidon. What are the algebraic models that have been proposed, and what does this mean for the random number derivation? Good. So basically, for those who are not familiar with Gröbner basis is basically a tool to solve a polynomial equation system. And how do we get a polynomial equation system? Basically, we have Poseidon or any primitive in a certain attack scenario, say a pre-image attack, and then we just model this as a system of polynomial equations. And this is exactly the first step of a Gröbner basis attack, find an algebraic model. Then the next step would be to actually compute the Gröbner basis, and this is typically a degree reverse lexicographic Gröbner basis. So with respect to degree ordering. Then as a third step, we transform this into a Lex Gröbner basis. And the advantage here is that we have this univariate polynomial in this Lex Gröbner basis. And this univariate polynomial we can just solve. Good. So there are several issues here. So the first thing is already the algebraic modeling, as we have seen in the previous talk. And as we will also see a bit later, there are a lot of round-skipping tricks that could be applied. And this might make the system that we are trying to solve easier to solve. Then for the second step, there have been recent works on how to actually skip or at least simplify this Gröbner basis computation step by choosing a dedicated weighted monomial order instead of this canonical degree reverse lexicographic order. And then for the second step, the Lex Gröbner basis, there are some replacements, but they have relatively similar complexities. Good, so let's start right away with this modeling tricks. For the modeling tricks, we have this skipping initial full rounds of Poseidon. The first work on that was from 2022 by Barillon et al. And they basically showed that for the initial Poseidon, they could skip the first two full rounds. And this assumed that there is no initial matrix multiplication. If you add this initial matrix, then only the first round can be skipped. So how is this done? Basically, one introduces a fine subspace after the first S-box layer. And this subspace is chosen such that when calculating backwards, it fulfills some input constraints. Say it is the inner part of a sponge, for example, the initialization. Then only recently, this round skipping trick, this one round skipping trick has been generalized to a CQK. So if we have more than one state element that is fixed in the input, and then you just saw the very nice talk about skipping more than only, or potentially skipping more than only one full round for Poseidon 2. Good. Then there are also partial round skipping tricks. So for the partial round skipping tricks, one chooses some affine subspace within the partial rounds. It is chosen such that the next few partial rounds can actually be skipped. And by skipping, we mean that there is a linear relation between those rounds. Good. And with this trick, at most t-1 partial rounds can be skipped if t is the state size. This round skipping trick always works. This is independent of the matrix that is actually used. How many rounds can be skipped actually depends on the state size and the constraints, inputs and outputs, so basically the attack scenario. One more thing about Gröbner basis analysis. So when all those arithmetization or the hash functions started, and then people started doing Gröbner basis cryptanalysis, what they did is they based the complexity of a Gröbner basis attack on the first step of this Gröbner basis attack. So the Gröbner basis computation with respect to this degree ordering. And at first, they took a bound called the Macaulay bound as a complexity metric. And unfortunately, this metric only is tight in case that the system is regular. And there has been a lot of proof in the last few years that typically those systems that come from arithmetization-oriented hash functions are not regular. So those bounds typically overestimate the complexity, and if you would now use it for deriving round numbers, it would underestimate the number of rounds needed to achieve, say, 125-bit security, 128-bit security. So what was done afterwards is performing small-scale experiments, because large scale is not doable, hopefully, if we aim for 128-bit security. So small-scale experiments mean we take small primes, we take smaller state sizes and less round numbers, and then we see what complexity metrics do we get for the individual steps in our experiments. And then we try to extrapolate basically those metrics to the real primitive instances or parameter sets. And hopefully, if our estimations are good, or if we're confident in our estimations, then there might be conjectures. And now for Poseidon 2, or for Poseidon, only very recently there was the first explicit Gröbner basis construction, where afterwards tight security estimates could have been given. And I think there will be a talk shortly. This is the algebraic CheapLunch, sorry. Good. So what are now the implications for the security analysis of Poseidon and Poseidon 2? So maybe we should, so the first point is that maybe we should start basing the complexity not on the first step of the Gröbner basis attack, but on the second step, so on the basis conversion, on this FGLM step, because it's often easier to predict what is the complexity metric in this case, and there now also exists a proof of this complexity metric. And then how could we potentially harden against those round skipping tricks? So the probably easiest solution would be, okay, just add rounds, but yeah, this might not be beneficial for efficiency. So one could also say, okay, we use an MDS matrix, and this for Poseidon 2 in the external rounds, but this would obviously be some trade-off between the efficiency using actually Poseidon 1 or Poseidon 2 with more rounds. Good, and for the partial rounds, this is always possible. In comparison to these full round skipping tricks, these partial round skipping tricks don't really come that much for free, so to say. Yeah, a possible mitigation would still be to add T partial rounds, but it's not strictly necessary. So what I have prepared here now is a table where we show the numbers, the round numbers for Poseidon 2 for some prime of approximately n bit size with a target security level of 128 bits. And in gray, you see the old round numbers, and in black, I have some updated potential round numbers. So this is not a suggestion, but just what would it look like if we now used the strategy to derive round numbers based on the second step of a Gröbner basis attack, so on the FGLM. And you might also notice that for the 31 and the 64 bit approximately instances, we also increased the number of full rounds just for the fact that here we don't have an MDS matrix, but for the 256 bit case, we have an MDS matrix in the external rounds. And finally, it's probably necessary to revisit the different security levels. So you might know that for Poseidon 2, there is this nice round number derivation formula. And this formula theoretically works for different security levels. And there have been studies on how the effect is actually if we increase the very, very high security level, say 1024 bits. And recently it has been shown that there we might need more rounds to actually reach this tremendously large security parameter. Good. So some further considerations. So we already heard about the text scenarios beyond zkK, namely compression versus sponge, pre-image versus collision. And one might also consider security in schemes. Then obviously Gröbner basis is not the only possibility to solve a polynomial equation system. So there are other ways recently also applied to Poseidon, and a bounty winner, I think, was a combination of interpolation and resultants, so zk2 problem, and iterated resultants, not applied so far, I think. Good. Then another open question is how do our small scale experiments scale to actually practical sizes? So we need more experiments on larger parameter sets. And finally, are there more models exploiting structures such as the structure of the prime, or as we have seen, the matrices or even the round constants? Good, thank you very much.
Thank you, Katharina. You had a table with the suggested number of rounds for Poseidon 2. Was a similar work done for Poseidon 1 as well?
Not yet so far, but I think in the next talk, Markus mentions some implications on the complexities for Poseidon 1 and Poseidon 2.
You mentioned at the end attacks based on the structure of the prime. So I think that's already something that was if the factorization of p-1 was smooth, then there was an attack. And of course, in practice, we want highly two-adic fields. So that puts a, you know that p-1 has a high power of 2. So what is known about the security of Poseidon in those cases?
Honestly, I don't know. So I have not yet looked into those specific cases, but more into this general Gröbner basis attacks.
This is a bit of a general meta question, but are you satisfied with the amount of cryptanalysis that's going into Poseidon in general? And if not, do you have like specific suggestions as to how we could improve things?
I mean, there can never be enough cryptanalysis, no? But I think it's very nice that there is a lot of cryptanalysis going actually into Poseidon. And I just recently made a comparison graphics on different zk-friendly primitives and the amount of cryptanalysis that is actually going into it. And I think by now Poseidon is on place 2, just after MIMSI. Yeah, so this is definitely a good direction, I think.
Okay, I'm surprised we're behind MIMSI.
Yeah, but there.
I'm surprised too, because cryptographic engineers just abandoned MIMSI after a few papers on it.
Yeah, I mean, most of the cryptanalysis is also statistical analysis. So statistical cryptanalysis and not so much algebraic cryptanalysis. So maybe that's also a way.
Katharina, so all this work is analyzing classical attacks on Poseidon. Are you also looking at quantum attacks?
No, this is just classical attacks.
So is anybody studying the quantum security of Poseidon? Isn't that's the whole point of moving to Poseidon, no?
Good question.
Well, there's some research on Gröbner basis attacks, like on a quantum computer, and there are like generic attacks non-specific to Poseidon, like how to improve several cryptanalytic methods if you have a quantum computer. But I think the overall consensus is that like the improvements that you have with the quantum computer on specific attacks is far smaller than the improvement that comes, for example, with the Grover search. So it's not a square root improvement. It's usually much smaller. So if you, for example, tolerate 64 bits quantum security, and if you already have 128-bit classical security, then you have this level of quantum security. So it seems that no super fast cryptanalytic quantum attack is known that is so much faster than the classical one. Well, of course, we can't exclude that it will appear, but so far the results are, the improvements are not that big.
Yeah, it's an interesting question. And if we are going to have another NIST competition, then I guess quantum security should be an explicit criteria in addition to zk friendliness. Katharina, thank you so much for your great presentation.
Thank you for having me.
Next up, we have Markus, who will talk about security margins.
Yes, thank you. Let me just maximize the screen. Hopefully you can see it.
Yep.
All right, yeah, thanks for the introduction. So let's start right away. So where are we at? First, let me start with like two sentences here. So the original version of Poseidon, which uses the MDS matrices, is not affected by the recent round skipping attacks. So there's the other round skips. You can always skip like one round. This is true, but the recent attacks do not affect it. So what does it mean? It retains its full level of security, of course, including also the margin. As we know now, this is a bit different for Poseidon 2 because it's affected indeed by these recent very nice results. But still, it also retains its full level of security, albeit, of course, the margin got a bit smaller. So there's now some natural questions we can ask ourselves here. Of course, the most pressing one is, what is the remaining margin of Poseidon 2? If we decide it's too low, how do we get back to the original margin? And should just everyone abandon Poseidon 2 and go to Poseidon 1? So let me give an overview here, a table. So I will explain later why these are very optimistic conditions from the attacker's point of view. Also, these are not pre-image attacks or collision attacks. These are attacks on a SQL instance where essentially just try to be faster in some instance than brute force would be. And still, we see that essentially we still have a hefty margin for most instances, and we are only 1 bit below the security level for the bottom right instance. 1 bit below because in this case, 4 times 31 is 124, not 128. Yeah, and about the table, you may also notice that instances with very small state sizes, which are usually used for the larger primes, they're missing simply because they're not affected by the recent round skip attacks. The reason being because the external layer is always an MDS matrix, even in Poseidon 2. So why are these instances very optimistic on these conditions? Well, first, in this recent paper, you essentially in some cases can skip a number of full rounds, and then you can skip part of a full round with the remaining, so by linearizing some remaining barriers. So in this case, I've rounded up the number of skipped rounds. Also, it's for the CQK instance, not for the full pre-image instance. We further assume a linear algebra constant of 2, where realistically we would have 2.3 or something. So this, of course, scales the complexities up again. And also all of this we're always talking about computational complexity, while specifically for those algorithms, the memory complexity is often very, very similar to the computational complexity. And in practice, the memory is a bottleneck much sooner. So this is also something which is often overlooked. But okay, let's say we're still not happy. We want to restore the previous margin, right? So there are different ways of doing it. So first, we can, of course, try to use different S boxes. Now, that's just a recommendation from my side, or an opinion. I would not do that because that goes against the idea of Poseidon, and it would also require a lot more cryptanalysis. We would move away essentially from the very simple design it currently is, at least with respect to the S boxes. We could also try to increase the number of partial rounds, but I would not do that either. We'll talk about this on the next slide. So the missing options are either we increase the number of full rounds to some extent, or we try to adapt the matrices, of course, because they seem to be the core problem of those round skipping attacks. So, okay, why are full rounds better? First, if we increase the number of full rounds, the impact on the attack complexity is usually larger than if we increase the number of partial rounds. The reason being that first, they are statistically relevant. The partial rounds, of course, they do something statistically, but we don't really use them in the statistical argument. And also in the recent estimates, and this is shamelessly copied from the skipping class paper here, it leads to a higher ideal degree if we increase the number of full rounds compared to the number of partial rounds. So this is from a security point of view. Of course, from the computational point of view, we can say that each partial round needs its own linear layer, of course. So we would need comparatively more partial rounds and more linear layers. So this would make the entire construction probably a lot more expensive. And also full rounds are more traditional. It's a hand-wavy argument, but it stands on decades of cryptography that using full rounds essentially is the cleaner way of doing it. And we have seen that they're much harder to skip than the partial rounds. Yeah, and what would the impact be? The impact would be minimal. For example, if we add just 2 full rounds, we would have an impact of 10 to 15% on the final computation. So it's not huge. Of course, this also applies to the witness size, right? Okay, so we can skip. We can increase the number of full rounds, but we can also try to adapt the matrices. To me, at least, it's unclear if it's possible to define a matrix which is provably unaffected by all the recent round skips and also as efficient as the Poseidon 2 matrix currently is. There's this direction given in the skipping class paper, It's heuristic. I'm not sure if it works for every subspace or just for those. But then, of course, we can say, well, let's just forget those more efficient matrices. Let's switch back to MDS. And years ago, this was quite bad because MDS needs like n squared number of operations and so on. But recently, we've shown we can do this actually better. So we can use something which is called like a circulant matrix. And it turns out that for most of the prime numbers we actually use in those proof systems, because they have such a high two-audacity and so on, we can actually define circulant MDS matrices for many different instances. It actually works very well. And once we have such a matrix, we can always do two things. We can decide to do some entity-based multiplication, which is asymptotically much faster than the naive approach, but it turns out actually in practice it's sometimes slower than the naive approach. Or we can choose a second option, which is essentially a Karasuba-based multiplication, and this turns out to be very fast in practice. And maybe we'll hear some benchmark numbers in one of the next talks. So this is all of that is not too bad, and actually makes Poseidon 1 also pretty fast. So let me come to the conclusion of this talk with another idea. This is not a recommendation of what everyone should use, but if you just focus on the partial rounds, which are not really the core of those skipping class paper and other recent papers, then we know that also the partial rounds are different between Poseidon and Poseidon 2. And in Poseidon 1, we have this equivalence where we can essentially take the MDS of the partial rounds and transform it into an equivalent representation. Then we don't have the full matrices anymore in the partial rounds, but we have like more or less random entries there. So in Poseidon 2, we solved it. We have a very efficient matrix also in the partial rounds. And because of this equivalent representation in Poseidon 1, there would be no security reduction, so to say, at least not that I know of, by taking just the full rounds of Poseidon, which have the MDS matrix, and the partial rounds of Poseidon 2. This should still be faster than optimized Poseidon 1, and should come with no security reduction. So this is one possible hybrid we can think about in the future. It may be a possible strategy here. All right, so I was very fast, so let's just come to the conclusion. Just summing up, so neither Poseidon nor Poseidon 2 are broken, and so this is not to take anything away from the results, which I think are very, very nice and very needed also. And I'm happy actually that those hash functions get analyzed so much. But yeah, the results also show actually that there is still like a substantial margin remaining, even under conditions which are quite optimistic from the attacker's point of view. If we are still not happy about that, if we are still like feeling insecure about Poseidon 2, then we can switch to the MDS or even to Poseidon 1, to the original spec, right? To avoid all of those, most of those problems. Like one round can always be skipped, but that's another topic. And it turns out that the performance hit, if we do that, is actually not huge if we use some modern or optimized implementations. So that's always a possibility, of course. Yeah. Thanks.
Thank you, Markus. You had this table with like, I guess, security margins for Poseidon 2. Could you quantify the security margins for Poseidon 1?
Mm-hmm. Yeah, sure. So Poseidon 1 will be essentially the second column here because we can always skip one round. And just more detail on the table. So the baseline here is not what we analyzed years ago. The baseline is the original round number without any skips, but still using the most recent estimates for the algebraic complexity of the attacks. That's the baseline. The second or the third column here is essentially skipping one round, which would apply to Poseidon 1.
Okay, got it. Any questions from the audience? I have a question around, the methodology of setting rounds. As far as I understand, the way that the industry works is that, the initial authors kind of make a best guess on the number of rounds, and then, there's like 10 years of cryptanalysis, and then eventually it becomes standardized or used in production. But like, wouldn't it make more sense to somehow revisit the number of rounds before standardization and before it's used in practice, after we have the 10 years of cryptanalysis, so that we can make a more informed decision when setting the number of rounds?
Yeah, so I agree totally. This makes a lot of sense. It's always like it's always a distinction between is the increase of the number of rounds just an informed decision, or is it because we feel insecure about it? And if it can be like phrased in the correct way, that indeed that's we are not insecure about the previous round now, but we make this informed decision, then I think it makes a lot of sense, of course. Yeah. But we shouldn't do it because we're afraid of the original round. Yeah.
I just want to say that cryptographic engineers hate changing parameters as part of the standardization process. First of all, because they have implementations, and so you end up with a thing like Ketchat 3 that is different from SHA-256. Ethereum people know about that. Also, I mean, it leads to kind of conspiracy theories, especially if you're reducing the number of rounds, then are you sort of weakening it deliberately or incompetently? Yeah. And yeah, we hate it. Just don't do it.
Another problem maybe is that, well, if a function is not fully in production and not fully standardized, it attracts much less cryptanalysis. So people are like less tempted trying to break it because, well, it's not a standard yet. Let's wait till it like becomes really a good target to break. So if you never standardize it and you just change the number of rounds, then you don't have like the best cryptanalytic minds targeted at it.
Okay, thank you so much, Markus, for this reassuring message that neither Poseidon 2 nor Poseidon 1 are broken yet, and there's no need to panic. Next up, we have Atharva, who will talk about CheapLunch.
Thank you. Yes, I hope you can hear me and see the slides.
Yep.
Yeah. So hi, I'm Atharva Phanse. I'm a PhD student at Simula UIB, and I'm going to talk about our work on cryptanalysis of Poseidon, which we call the CheapLunch attack. This will be more of a high-level overview of the ideas of the attack, and some of the things have already been mentioned in the previous talks. So this is a joint work with some other co-authors from Simula UIB and some from France. And our work can be found on the preprint archive of ICR, and it's also currently under submission. So the setup, as we know, there is a push for cryptanalysis of Poseidon, especially the Poseidon cryptanalysis initiative by Ethereum, and our work was also supported by one of the grants. There's a need for understanding the security of Poseidon against different types of attacks, and algebraic attacks are one of the main attack vectors. But there are some open questions in the space, which is what our work focuses on. And we also don't break Poseidon fully, but what we try to do is to improve the understanding of how the algebraic attacks work, so that it gives us a bit more confidence in the overall security of Poseidon. So the Poseidon hash function is set up in the sponge mode. Here we're working with the tuples of length t of elements in the finite field. And p is the Poseidon permutation that's getting repeated sequentially, first absorbing the messages, each of block length t, and then squeezing out the hash output. And these tree branches are further divided into rate r and capacity c. And to understand the security of this hash function in the sponge mode, we would like to focus on the security of this permutation, specifically that's getting repeated. And one of the common methods to do that, as it's already mentioned, is the constrained input, constrained output, the zkWHIR problem. So here we want to find an input vector where we have zeros in the last t minus k places, and some values x1 to xk coming from the finite field, such that when the permutation is applied, we get k zeros in the output. And if zkOK problem is easy to solve, then it's possible to set up attacks, pre-image or collision attacks on the entire sponge hash. So for zk1, there's a bit more clarity. We have more understanding on how the attacks work, not just for Poseidon, but in general for other hash functions in this space. But for zkOK, when k is bigger than 1, there's very little understanding, and there's more questions to be answered here. But why is k bigger than 1 relevant in the first place? So naturally, we have that k is less than the number of branches. And when we have a smaller underlying field, the values of T, R, and C have to be larger. So that leads to larger possibilities for k, and then more zkOK problems are relevant. But even for just k equals 2, we need to have better understanding of the attacks. So how do we solve this zkOK problem in an attack, and what are the open questions there? So this problem of finding the x1 to xk, we consider them as variables, and we construct some polynomials f1 to fm using the zkOK output constraints and also the round by round structure of the Poseidon permutation to make these polynomials. And then essentially the problem of finding x1 to xk, the problem of solving the zkOK problem, is then equivalent to finding roots of these polynomials. And to do this, we use some tools from algebra. So we work with the ideal generated by these polynomials in the multivariate polynomial ring. And then for this attack, we find a special generating set for this ideal, which is called the Gröbner basis of the ideal. And this Gröbner basis is tied to the monomial order, which is an order that we can define on the elements of the ring. It's just a way of comparing two monomials, which one is larger and which one is smaller. And there are different ways of defining these monomial orders. So the Gröbner basis is also dependent on the order. So for some monomial orders, it's easier to compute the Gröbner basis, and for some it's more difficult. And that's what we do in the first step of the attack. So we compute the Gröbner basis in an easy monomial order. Then in step 2, we convert this Gröbner basis to this particular monomial order, which is the lexicographical or lex order. And then here we often have a univariate polynomial, which gives us value for one of the x1 or x1 to xk. And then we get the solution. So often the step 3 is negligible in terms of complexity in the attack. So it's important to understand how step 1 and step 2 behave and how the complexity behaves to understand how difficult it is to launch a zkOK attack using Gröbner basis. So the complexity of step 1 depends on this value called degree of regularity, DREG, and step 2 usually depends on the ideal degree or DI. Both of these values depend on the structure of the ideal, the polynomial system that we create to begin with, and also the monomial order, because the Gröbner basis is connected to the monomial order. And it's quite tricky to get these values right, as it's already mentioned, that the systems often are not regular, and extrapolating from experimental values to large round numbers can also be difficult, because usually computing these values is same level of difficulty as actually launching the attack. So we would need some extrapolation from small scale experiments to find out what these complexities are for full rounds of Poseidon. And this is where some of the previous zkOK analysis has maybe struggled to get this complexity estimate right. And then the ideal degree that was observed in experiments was also lower than the theoretical estimates, which leads to also the question, is step 1 the bottleneck of the attack, or is it the step 2? And these are the questions that we try to solve. So going into a bit more details of the technicalities of the Gröbner basis. So the core idea is that we use a weighted monomial order And since the Gröbner basis is heavily dependent on the choice of the order, this gives us certain advantages, mainly that the polynomial system that we create can essentially be split into two parts. One part that has a lot of co-prime leading monomials, and the other part that does satisfy these regularity assumptions that are not satisfied by the host system or in some other modelings. Also, the leading monomials of this first part do not interact with the leading monomials of this second part. And this structure is what gives us the CheapLunch attack. So let's say we have this polynomial system that's constructed using the zkWHIR problem on Poseidon. We have some polynomials P1 to PRP from the partial rounds. We have the K output polynomials from the zkWHIR constraint. And essentially, most of these partial round polynomials are the ones that have this property that the leading monomials are co-primed. And then we essentially don't need to compute the Gröbner basis on this part of the system, which means we only need to solve the system, a smaller system, which is P1 and this final K polynomials. And even here, we can make further simplification that we only need to compute on the highest part, so even smaller part of the system, because we again rely on some of these regularity assumptions. So as a result of this, step one of the attack, which was actually computing the Gröbner basis, is now needs to be done only on the smaller system. So it is much cheaper than expected. So then the bottleneck of the attack is transferred to step two. And that is the one that should be used to compute the number of rounds. Also for step two, since the complexity, as I mentioned, depends on the ideal degree, and the bound that was observed experimentally was smaller than maybe some other modelings. And we do actually get this bound in our theoretical calculations as well. So what does this imply for Poseidon? So the Poseidon system in our modeling is regular. So it does satisfy the assumption for a small scale tests. And this assumption is essential when we want to estimate the complexities. This also gives us the better understanding of the difference in contribution of full rounds versus partial rounds, the way they contribute to the immunity against algebraic attacks, as we can observe in the ideal degree that the partial rounds contribute less, because those are the ones that we can separate when we make the smaller system. And in our work, we show that Gröbner basis computation in step one is much faster, so then the bottleneck should be step two. There are also some more results that are covered in our work, but I didn't cover in the presentation. Some discussion on the round skipping tricks, but much stronger results here are already covered by Àlex. And we also can use this CheapLunch structure to further study the step two. So once we transfer the bottleneck to step two, we can also give more refined analysis of the complexity of step two. And this can be found in our work. And to summarize, as I said, for realistic parameters, we did not find any attack, any improved attacks on full Poseidon. But our work gives us more concrete understanding of the behavior of the complexity against a complexity of the algebraic attacks. So that gives us more confidence in security of the hash function. And thank you.
Thank you. We have a question from Dara.
Yeah, so a partial run's a bad idea. So is the security that they provide sufficient to justify using them given their cost? So the original premise behind the design was that it was beneficial to use partial runs because they were sufficiently cheap and they still gave enough security to justify using them. Do we think that premise was incorrect?
No, so I would maybe go to this. So it's not that the partial rounds do not necessarily provide security against attacks. It's just that the contribution is much less. But in this ideal degree, partial rounds do have a contribution, even less, but they do have contribution. And ideal degree is what we use for the estimation of step 2. And already the full rounds plus partial rounds, so this overall ideal degree is large enough for realistic parameters that this CheapLunch structure is not a problem so far. So I would say,
so looking at that formula, basically partial rounds need to be at least k times cheaper than full rounds in order for it to make sense to use them, right? If this is now the bottleneck. Okay, so what is k here?
K is the k in zkWHIR.
Right, zkWHIR. So how does that relate to the parameters of Poseidon? Is it the state size or?
Yeah, exactly. So it also depends on it depends on the state size and also the rate and the capacity. So the zkWHIR problem is just on the permutation, and then different. So you have zk like k1 in input and k2 in output, and different combination of these can be used for like different attacks. So it's possible that maybe if we have large field and only 3 state size or 5, so then we only care about k equals 2, k equals 3, and then maybe it's not a big factor. But yeah, so this k is coming from zk problem. So then that case,
but the k for the zk problem is not going to be greater than the state size, right?
Exactly. Yeah.
Okay, and the benefit that you get from partial rounds is that you're only doing one S box instead of state size X boxes. So if we have, I see. So it does still make sense, because whenever k is less than the state size, we can expect the partial round cost is worth it. Okay, I see.
Katharina?
Yes. So very nice paper. Do you see any chance that you could actually combine the round skipping tricks with the CheapLunch system?
Round skipping
inherently impossible.
Well, because so our work is like quite flexible for the like the k in zkWHIR. So, and I think that's the part that's like the restrictions for round skipping are like it's not applicable for maybe all zkWHIR. So yeah, I haven't looked into it much yet, but I think it should be possible just to like start the zkWHIR Gröbner basis from
Yeah, because you still need to find the monomial ordering, right? That then basically fulfills this splitting property that you have, that the first part is basically a Gröbner basis and the second part is at least has some nice properties that you can then use.
Yes. So yeah, that is true. So we do need the weighted monomial order for the CheapLunch work. So yeah, I think I'll have to look into it too.
Just wanted to know if there's anything ongoing in this direction already. Thank you.
Thank you.
Fara, as a kind of latest generation PhD student, is your intuition that AI will play an important role in cryptanalysis going forward? It seems like a good match, especially for Poseidon, because it's so highly algebraic. Are you starting to use it already?
Not in the attacks itself. So in the algebraic attacks, I don't see how yet that it can be improved, that it can improve the attacks, I think. But yeah, this I could be wrong, of course.
Because I've been criticizing, lattices, for example, as not being post-AI, because potentially we have these like super smart mathematicians in the future that could find hidden structures in lattices. But maybe the same argument just applies to Poseidon as well. Sorry, Dara.
I was just going to say that AI is great for actually searching the literature, because search was terrible of the academic literature, and now it's great. So yeah, you're not sort of redoing work that people did 10 or 20 years ago, which you quite often were.
Yeah, and for those factors, yes, I have used. I would agree that AI is definitely quite useful for learning some new things, new topics. But in the attack itself, yeah, I'm not sure.
Got it. Thank you, Atharva. Next up, we have Léo, who will talk about state-of-the-art cryptanalysis of Poseidon.
Yeah. Do you see my screen? You hear me first?
Yeah, your screen
Do you see my screen?
Yes, perfect.
All good? Okay. So, yeah, thanks for having me. I will try to give an overview of the state-of-the-art on the cryptanalysis of Poseidon. There will be some overlap with the previous talks, so we try to skip what needs to be skipped. Just as a small background, I'm a symmetric cryptographer. I have worked on the cryptanalysis of symmetric primitives for quite some time now, and so that's going to be my perspective on this. So yeah, what do we know about the security of Poseidon? And I will start with my conclusions, so you see what I'm building up to in this talk. At this stage, Poseidon is one of the safest arithmetization-oriented permutations I can think of, and I can think of quite a few. Unfortunately, that's not saying that much. There's still a lot of unknowns when it comes to the behavior of the relevant algorithms. So I'm going to go over the main threat posed by polynomial system solving, as has already been said in the previous talks. And then I'm going to focus specifically on Poseidon. So sponges, I think by that point, we are all quite familiar with how they work. We want F to be good, where F is the permutation used here. And what does it mean to be good? It's actually very hard to define. For a block cipher, we know that it means that you want the key to be hard to recover. But for a public permutation, you don't really have that notion. So one of the proxies we use, which is not perfect, as was pointed out by Àlex in his talk, is this zk problem. So where you want to have an input with k zeros that is mapped to an output with k zeros, constraint input, constraint output. It's not sufficient that this zk problem is hard to say that the permutation is good, but if it's easy, then it is bad. That's there's an implication, but not an equivalence. So in order to be able to trust Poseidon, we need to understand, the missing word is understand, the complexity of solving this zk problem. And in particular, what we would like to know is how the complexity of solving zk scales with both the number of full rounds and the number of partial rounds. So in symmetric crypto, we have a lot of attack techniques at our disposal. You have in particular statistical attacks, which tend to work really well against classical F2 primitives, like linear attacks, but they're basically relevant for Poseidon because it's a hash function. And differential attacks, which are not a threat because of the good differential properties of x to the power d, modulo the potential poor choice of a linear layer. So that was some attacks that were published when the first Poseidon came out, that you had bad choices for the linear layer. It's stuff that's much more understood now when you have some tools that can test if your linear layer is good or not. And of course, now we also have algebraic attacks. Or I need to switch the light back on. Yeah, there we go. We have algebraic attacks, and this is much less clear. While we have a good toolbox to understand to estimate the complexity of linear attacks and differential attacks, for algebraic attacks, not so much, and that's the main problem we have. Well, how does it work if we want to attack round-reduced Poseidon? So first, we need to encode our zk problem into equations, and then we need to solve these equations. So we're going to use polynomial system solving techniques, POSO, to solve the system and thus obtain an input for the permutation that has the properties that we want. We have been over this already a couple of times in the previous talk, so I'm not going to insist more. And what you actually do is that you use a round skipping trick first. So you are not trying to solve to write it in this way, you start after a few rounds, propagate, and you skip the first rounds using some heuristic. We can skip much more than we thought. So I really want to congratulate Àlex and his co-author on their work that was presented earlier this afternoon. It's really, really good work. They really go much further than was previously thought possible, because they managed to skip 3 full rounds, if I understood correctly, which is a lot. For Poseidon 2, using the classical techniques that we introduced in our 2022 paper, we would be able to only to skip 1. So that's really substantial. But that's the round skipping part, which is very hard to understand, and we just had a breakthrough, so obviously we don't understand it well. And then we need to solve, and it's also a mess. So initially, the lower bounds for solving for the complexity of solving were based on the time needed to compute a Gröbner basis, but this is completely wrong, because we can get this completely for free, actually. So the initial estimates were basically useless. And another issue which is arising, which has started to arise much more recently, is that we try to estimate the complexity of off-the-shelf algorithms that are made to solve this Poseidon problem, but they tend to be less efficient than tailor-made ones. And so now you have these resultant-based algorithms, you have the use of the Grave transform, and these can have lower complexities than these off-the-shelf algorithms. And since they are, these algorithms have been made specifically for Poseidon, we don't have a literature on their complexities because they are brand new. So their precise complexity remains actually quite mysterious. So my conjecture, which is most likely correct if we put C equal to omega, but that's an upper bound, is that if you want to solve a zkK instance of Poseidon and that your S box is of the form x to the power d, then your time scales with this quantity here. So there's not much happening, actually. This d to the power k times rf plus rp, that's the ideal degree that Atharva presented in his talk just before me. That's actually where it comes from. That's the ideal degree. But you skip some rounds. So this is captured by this, this factor here. So you have this ideal degree, but you divide it by basically the number of S boxes that you skip. And then once you have done this, you still need to do some linear algebra, maybe, or to do something to get your actual solution, to well, your actual univariate polynomials that you can actually solve then to get your solution. And this is where also some stuff can happen. So what you can always do is something like FGLM, which is going to have a complexity that corresponds to the linear algebra constant. So, you know, like 2 to the something, 2 to the 7, 2 to the 3, if you're very optimistic. But if you look at resultant-based algorithms, it can be lower. If you're in the univariate case, then basically C is equal to 1. One of my students is working on a resultant-based technique for zk2 for Poseidon, and the complexity is corresponds here to something that's lower than 2, where C is strictly lower than 2. So it's hard to know exactly what we can use as the value of C. So I'm going to see what happens when we plug in some numbers. So first, before I conclude, I will allow myself a small complaint to the Poseidon 2 designers. I was trying to get parameters, and this is what you're met with when you read the paper. So I just took quantities from a table. But first,
terrible for implementers too.
Sorry?
It's terrible for implementers too.
Yeah, I can imagine, yeah. There is, to be fair, there is a script that gives you parameters. But anyway, for Poseidon 1, so again, I am not saying that attacks with these complexities exist. What I am putting in this table is an estimation of this quantity here, of this quantity that you want to be higher than your security level if you want to have some security arguments. And I'm putting some estimates depending on what values we use for this quantity C here, which corresponds to the solving step, and the number of rounds that are skipped. So for instance, here, this quantity here is perfectly realistic it corresponds to univariate solving, where you don't skip any rounds. It's in this case, it corresponds to an attack. That can be relevant or not depending on your field size, but that's how it is. Here, for instance, we are very pessimistic with the complexity of the solving step. This is just the omega from linear algebra, but we are widely optimistic about the number of S boxes that can be skipped. Like this is, we could do that, but maybe we can. So as we can see from Poseidon, in all of the parameter sets that I have looked at, and all of these guesses about the parameters of the complexity formula, we are okay. Even in the cases where we are not okay, which is when this is below the intended security level, we are not that far below.
Can you go closer to the microphone, because sometimes you're getting a little bit garbled.
I can try. I'm not sure which microphone is being used, but yeah, don't hesitate.
That seems better.
Okay. So basically for Poseidon 1, even far-fetched scenarios are okay. And we will see where the difference comes from. For Poseidon 2, it's more complicated. So for Poseidon 2, you have much more variety in your parameters because the field size varies a lot more. Field size of 31 bits or a field size of 256 bits mean that you're looking at a primitive that has widely differing state sizes, which then has a huge impact. Because when you have a small field size, it means that the attacks that are relevant will be of the form zkK, where k is much bigger. Because if you want to solve for zkK when k is equal to 1, when your field size is of 31 bits, you will just brute force, actually. You're not going to do all this clever stuff. You're more interested in higher values of k. Conversely, in the case where the field size is much bigger, then you care only about the case k equal 1, for instance. So you have some sets of parameters that in this table that are probably unlikely to occur. But so you have some potential situations where this bound is not high enough. I am not saying that attacks matching this bound exist. I must insist. I'm just trying to see the behavior of the different parameters here. The big difference between Poseidon 1 and Poseidon 2 lies in this difference in field size. Since the field size is smaller and you have then a state size which is much bigger, then it means that your partial rounds are much weaker than the full rounds. That's the first difference. And second, since you have a much bigger state, you have a lot more degrees of freedom to skip rounds. So your full rounds, in a way, offer you less protection. So that's what's happening here in these red values here. That's why they are here. Since I have put a number of round skip, which is, again, I don't know how to do that, but which scales with the state size, which in my opinion makes sense since you use these degrees of freedom, then you're hit harder by these round skipping tricks. I think that's where Àlex was going when he said that older Poseidon was more secure because of its bigger field size. It's because the round skipping is much harder when the field size is bigger. On the other hand, when the field size is bigger, the solving step is simpler because k is smaller. That's what hits you. When you want to do the actual solving step, if you're trying to solve for many variables, then you have to use your FGLMs or other such algorithms, and then your quantity C here is higher. So there is like a double bind type of situation where you want to have a small state size so you cannot skip round, and so the round skipping step is not very efficient, but you also want to have a large state size so that the attacker has to solve for a large k and thus has to use less efficient algorithms for the solving step. That's just how it is.
Emile, did you have a question? You had your hand up.
Yeah, I think you phrase it as a Poseidon 1 versus Poseidon 2 issue, but it's, if I understand correctly, it's really linked to the field size and state size. It could be also applied to Poseidon 1 with small field and large state, sorry.
Absolutely.
Okay.
Absolutely. So during the introduction, I would disagree with the idea that Poseidon 1 well, Poseidon 2 does not inherit the cryptanalysis of Poseidon 1. In my opinion, the two of them are indeed super similar, and it's completely fair to call Poseidon 2 Poseidon 2. The big difference comes from this difference in parameter sets that are considered. And the strongest cryptanalysis results on Poseidon 2 also come from something else, which is that if you look at the speed of research in the area of polynomial system solving for symmetric crypto, when we designed Anemoy in, I think it was published in 2022 or 2023, it was prehistory. By modern standards, it's completely obsolete. Our security arguments, by modern standards, the standards of 2 or 3 years later, are very bad. Like, we can do much better now. So I think a big difference in the cryptanalysis is these recent improvements in the understanding of algebraic attacks. It's not so much an inherent property of Poseidon 2 compared to Poseidon 1. They are more efficient against Poseidon 2 because the field size is smaller. But yeah, I literally use the same spreadsheet-like thing to generate both tables, because Poseidon 1 and Poseidon 2 only vary based on their parameters. I would argue that Poseidon 2 is a particular case of Poseidon 1. One of the big differences.
I'm a bit confused. When you say that the field size is smaller, do you mean for the challenge problems, or because I mean, do you mean for the challenge problems? Because I mean, if I have a particular field that is chosen from completely different considerations for my protocol, and I'm deciding whether to use Poseidon 1 or Poseidon 2, then the field size is fixed.
I'm not sure I got the question. If you have a different field, then I mean, so the big difference between Poseidon.
I'm not sure why you're saying that the field size is smaller for Poseidon 2.
So I had a quick look at the spec of Poseidon 1, and they seemed to really focus on these elliptic curve fields. But I think the spec could also be applied for a smaller field size. Yeah, there is more emphasis. Okay. There is probably more emphasis on the smaller fields in the spec of Poseidon 2. But I agree with you. Another big difference, if you look at the two tables, is that RP is partial rounds. Here you have tens and tens of partial rounds. Here you have fewer. That's also one of the big differences, in my opinion. But so yeah, my conclusion is that so at this stage, yeah, Poseidon 2 seems safe. Poseidon 1 also seems safe, because I would argue that they're really the same thing. The problem is that there is not much room for error. So there was recently this breakthrough, I call it a breakthrough, on the round skipping side. So who knows how much better we could make it. And the solving algorithms, we shouldn't assume that they're going to have a complexity. So we should absolutely assume that they have a complexity that scales with the ideal degree, as Atharva eloquently argued. But we shouldn't assume that it will be raised to an exponent, which is omega, the linear algebra constant. Because we have attacks where it's not the case, as a matter of fact. So omega is an upper bound, but we don't really have a lower bound at this stage. So if we manage to lower it substantially, we would need to have to lower it substantially from 2.7 to 1.5 to potentially have issues, and to also have huge increases in round skipping abilities. So I would like to be able to find arguments on both sides, but it's I'm afraid I'm going to have to end on this not so optimistic note. Thank you.
Thank you, Léo. Thank you for your honesty and food for thought. We're a little over time, so we're going to try and move to the penultimate presentation by Dmitry, who will talk about the bounds on round skipping as well as the bounties.
Hello. Do you see my screen?
Yep.
Okay, great. So I'll be talking a little bit on round skipping and a little bit on the bounty program we plan to have for Poseidon initiative this year. So little kind of a positive note on round skipping compared to like this, some kind of devastating news we have heard. So basically how I explained to myself the recent attack. So basically, if we enforce certain conditions in the state, and these enforced conditions are marked with very similar constant values around the S box, and you can see that in order to enforce these constraints, you spent exactly 4 degrees of freedom per round. Well, this 4 comes from a particular structure of a truncated differential we have for the linear layer. And this number 4, it allows us to say that we can exhaust our degrees of freedom after skipping about like 10 over 4 rounds, but we still have to kind of spend some freedom for guaranteeing output or input constraints. And because of that, the security margin is decreased by 4, or in some case, 5 full rounds. So if we look in further details, what has caused this, sort of high probability truncated differential, which allows us to set an algebraic variety in later rounds and propagate it up through the linear and nonlinear layer to the upper rounds, then, it's of course non-ideal diffusion was exploited here. The fact that MDS matrix has a certain eigenvector, but this eigenvector is just a specific case of non-ideal diffusion, and actually we can relate the existence of such transitions, which we call differential trails, to general properties of matrix M. And here we hope to have some positive results. Concretely, in the ongoing research, we show that all existing round skipping attacks, they're reduced to 2 conditions. So basically, first of all, there must exist a certain differential trail with few active S boxes, and the regular differential trail with at least that many S boxes, and also there must be a sequence of states satisfying certain algebraic conditions. And the number of conditions is proportional, around like half of the number of active S boxes. And this is all very similar to the rebound attack, for those who remember like AES and AES-based functions and ciphers and hash functions. And most importantly, we can get an interesting property. So the branch number for a matrix M is actually the maximal sum of non-zero elements in X and M times X. And for the branch number, we can actually upper bound the branch number by 4t over M, where M is the number of rounds you can skip. It means that for the maximum B, you can't skip that many because M must be small enough. And based on this theorem, you can simply state that if the linear transformation is MDS, that you cannot skip 4 rounds. The question is whether you can skip 3 rounds. It's an open question. It depends on the particular MDS. And I think we can design such an MDS where you can skip 3 rounds. Maybe it will not be the fastest attack, but still, like with this property in hand, we can upper bound the power of round skipping attacks. And for MDS matrices of Poseidon 1, we can have some kind of sort of provable bounds on the security against this kind of attacks. And that's a positive result. Another sort of positive thing is that we announced a bounty program for this year. The full details will be published early next week, I think on Tuesday, and the bounty will consist of 2 big parts. So one part is new challenges based on the usage of Poseidon in protocols and the SICO problem. And the second part is what we call ultimate prize. It's Poseidon 1 prize, which is aimed to find partial collisions. Well, as you may have guessed, the task is to find the collision not on the entire output size, but on a subset of field elements. And of course, the difficulty of this problem, it grows within a number of field elements. The concrete instances will be published on Tuesday. And of course, to prevent searching for such collisions in advance, the instances will have a short seed to prefix all hash inputs so that you cannot pre-compute the numbers in advance. So it all will be published around Tuesday on PoseidonInitiative.info. And later, the ultimate price will have its own website. So little formulas for the problems that we're going to have. Actually, there are several interesting things. So one challenge that we'll see is to find a non-zero string for the input, so that the total number of zeros in the input is not more than D, so that when you hash it and you interpret the outputs as positions, the original string in these positions must be 0. So basically, find the string so that when you hash it and you look at the outputs, the outputs point to 0 positions in the string. And of course, difficulty depends on D, and it all relates to usage Poseidon in the Fara protocol. The second interesting challenge is the code zero test. This is related to usage of Poseidon zkWHIR, and it's basically about finding a polynomial for which, so that if you hash this polynomial, then the output is its own root. So basically to find the polynomial so that the hash of the polynomial is among the roots. And of course, you can also upper bound the probability that it happens, and will select the instances so that it's difficult enough for people to try. And the collision challenge for which there will be a big prize. It's kind of regular collision property, find two inputs so that they are equal in up to T output field elements, and the total price fund is close to 1 million, and it grows with every field element you are able to collide on. That's actually it. That's the summary of my talk, and I'm ready to answer the questions.
Quick question on the portion which is not the Poseidon prize, but the 150K. Is Poseidon 2 going to be part of the scope, or are you also focusing on Poseidon 1 there?
Yeah, the plan is to focus on Poseidon 1.
Okay.
So, and we expect, of course, that the methods will be applicable to Poseidon 2, but as long as our kind of main idea is to try to break Poseidon 1, then I think it makes sense to specify only Poseidon 1 as a target.
And for Poseidon 1, you're focusing only on Coratger, right?
Yeah, well, to narrow the scope. Yeah, of course, we can describe any more, but it will make verification difficult and so on. I don't think that selecting Coratger, it makes the competition kind of unfair or make it more difficult to define something. I think one big advantage of Coratger is that the degree of the S-box is small, so that you can actually penetrate more full rounds. Katharina?
Yes, about the challenges. Does it make sense to maybe also have a challenge regarding the matrices in the partial runs? So basically what Markus mentioned, that the partial runs or the matrix in the partial runs used for Poseidon 2 should be as secure as the MDS matrix in Poseidon 1 case?
Yeah, well, probably it's a good question. Maybe there should be an award. So I think that it's in the plan to award a paper that will have this question answered, basically, whether we can use a non-MDS metrics for Poseidon 1 safely in partial rounds, because it will benefit the optimizations. So not a challenge, but rather like a grant or a gift to whoever answered the questions positively or negatively.
Maybe this has been already said, but to be sure I understand, the choice of the MDS matrix is totally free?
No, we'll specify it.
Okay.
Yeah, I don't think it's free because, well, it will have a big state and it will be difficult by itself to verify that the matrix is MDS. So probably we will not bother with it.
Okay.
Emile, might be worth coordinating with Dmitry so that whatever MDS matrix you use or whatever you think is reasonable is potentially also used for the prize. Thank you so much, Dmitry, for these 2 pieces of good news / hope. And we're going to end off with another piece of good news regarding the Poseidon benchmarks from Thomas.
Can you see my screen?
Yep.
Yeah, perfect. So I will give a short presentation about Plonky 3 and our Poseidon 1 benchmark, and I will give a brief word at the end about another project called Plonky 3 recursion. So I will go very quick over the slides. You can check later if you want, but this has already been presented in extent, so I will not go through it largely. But what's Poseidon? Basically, it is a hash function built for snarks that is very efficient inside circuits. On the contrary, SHA-256 and Ketchak are more difficult to handle within snarks. And so that's why we are choosing Poseidon for our work. The problem is that with the recent attack, we started to check Poseidon 1 again from a code perspective and from a benchmark perspective to see if we can make it fast and try to limit the slowdown when compared to Poseidon 1. It is important to understand from an implementation perspective what's changed. So basically, between the 2 versions of Poseidon, we have the same S-box, the same run count, the same security, but only the mixing layer changed. And so we have this dense matrix multiplication in Poseidon 1 with an MDS matrix that is very costly and that has been rendered very cheap inside Poseidon 2. So we have to deal with this and to find solution to make this MDS stuff tractable. That's why with the naive things, we have like a lot of multiplication, and we are trying to find techniques to reduce the number of multiplication from n square to something more tractable. So the MDS matrix that we are using is circulant. This means that each row is a shifted copy of the first one. And this specialized structure unlock fast algorithm. So we are using Karatsuba and potentially FFT-based algorithm. So these are the 2 main techniques that we are exploring inside Plonky 3, and mainly the Karatsuba convolution. Here I have recapitulated all of the fields that are available inside Plonky 3. So you have baby bear, koala bear, Mohsen, Goldilocks. So these are listed there. These are the main ones that we support in Plonky 3 right now, with a number of bits right there, and the algorithms that we are using for Poseidon 1. So mainly Karatsuba for everything, and for Goldilocks, Karatsuba or FFT. For the larger widths, we are using FFT, but we haven't studied that much this part, because for all of our application, including lambdaVM and the new Lean consensus, we are using koala bear fields, so that is our main interest right now. So Goldilocks, let us say, it's less studied. Here you have like the round configurations that we are using inside Plonky 3. So basically you have all of the widths that are tested for all of the fields. So baby bear, koala bear, Goldilocks, and Mohsen. You have the Xbox degree, the number of full rounds, the number of partial rounds. And what is interesting to notice there is that the number of full round and the number of partial round is the same for both Poseidon 1 and Poseidon 2. Only the linear layer differs. Here, I think that this is the most interesting slide, because these are like the benchmarks that we have run with Poseidon 1 and Poseidon 2 on an Apple Silicon, more precisely M1 Pro. And this is very important because I think that if you run with an M4 or something more performant, you will get completely different numbers from my experience. But basically there, you have all of the fields that I've summarized. You have each time like a Poseidon 1 version and a Poseidon 2 version, both for scalar and Packel version. So this means that each time, this is important to have the number per permutation. This is what you have there, because for 31-bit field, you have 4 lanes, while for 64 bit field, you have 2 lanes. So what is important to compare there is the numbers per permutation. This is recapitulating there. And what you can see, and what is interesting, is that more often, like the slowdown is 2x when you compare Poseidon 1 to Poseidon 2, right there. So this is a bit of a slowdown, but we expected at the beginning much more. So finally, this is a pretty good news. Here, like if you want to check after, you have like the precise benchmark for the scalar version with all of the slowdown line by line, and also the same thing for the packet version. But as you can see there, let us say the average slowdown is 2x for Poseidon 1 for the packet version. This is the most important one because in lambdaVM, we are always doing Poseidon in a packet form. That means that we compact things, then we do Poseidon over 4 lanes, and then we unpack things. So that is the good news about the benchmark, because at the beginning we expected something much worse. And finally, with some techniques, rearrangement, packing formats, SIMD, and a bunch of tricks, we managed to have like a 2x slowdown, which is not dramatic for our use case. And so finally, I want just to give a word about another project that is inside the Plonky3 GitHub organization, but as a separate repo. This is the Plonky3 recursion project. So that is a project maintained mostly by Robin and initiated by the Polygon cryptography team initially, and now mostly maintained by Robin. And inside this repo, you have a recursion based technique based on Plonky3 on its own. So what does it mean? It means that you can verify a proof inside a stack circuit. So this enables proof composition and multi-layer recursion. So the basic idea is that you have a proof, you construct a circuit based on this proof, and then you proof this circuit. So that allows you to do some recursion and some 2-to-1 aggregation. All of that based on Plonky3. So we are importing all of the primitives of Plonky3, and we are doing recursion based on this. So that is a very interesting project, and you can imagine that this is a bit the same thing that we are doing with lambdaVM, because the goal is the same, to be able to handle some recursion of proof. But this is on a different approach, because there it is a circuit-based approach where you are building your circuits. This is not a VM. While on the lambdaVM side of things, we are building a minimal zkWHIR with a specific DSL, so a language specific to express your program in this language. So this is a different approach, but this is very, very interesting for us to have a comparison between the two. And so if you want to check it out, for now, like the project is very simple with 4 basic crates, a circuit crate where you can build your circuit from basic operations like mul, had, and all of this. Then you have the circuit prover where you can generate proof for those circuits. And then you have the recursion part where you verify a proof inside a new circuit to do the recursion pipeline. And finally, we have a Poseidon 2 hashing inside circuits to handle Poseidon 2 precisely. So, but we want for sure in the near term to support Poseidon 1 as well, with all the discussion that we had today during this call. So if you want to check it out, here you have the link of the GitHub repo. And yeah, thank you for your time, and like don't hesitate to ask questions or reach out.
Perfect, thank you, Thomas. We have 2 questions. Have you considered Tomb Cook, I guess, as an alternative to Karatsuba and FFT?
Yeah, we have tried these things. For now, we haven't seen that much benefits. We have cooked different techniques, and this is the most optimized that we have for now. But
intuitively,
yeah,
intuitively, I would expect Tomb Cook to be better than FFT. And then the question is between Karatsuba and Tomb Cook. But I may be wrong.
Yeah, we have checked, and for now, we haven't seen any particular improvement. We have seen also that things depend a lot on the width that you consider for Poseidon. We are not, for example, if you take like Koala Bear for Poseidon 1, we are not using exactly the same tricks for 16 and 24 widths. So sometimes that can vary because of the size of the matrices that you also about.
And final question from Hector. What is the on-circuit overhead of Poseidon 1 versus Poseidon 2?
I think that this is most like a question for Emile, but I don't think that this is dramatic at all. I don't know, in VM, I think this is the same order of magnitude as the 2x.
Yeah, I would say so. If you prove your Poseidons via an R where you commit to a bunch of columns and then you prove that the relations are valid. Honestly, I don't have a clear answer, but the 2x from Thomas makes sense to me. But what I can say is that if you use zkWHIR to prove Poseidons, basically you will use like a bunch of sum checks to prove the cube transitions, and you can move out the linear layers out of the sum checks, and in some sense you will only prove cubes, and so you will not see any slowdown moving from Poseidon 2 to Poseidon 1. TLDR, using zkWHIR, Poseidon 1 is as fast in circuit as Poseidon 2.
And also maybe final word on this, I think that for our application that is in VM and XMSS aggregation, the cost of proving Poseidon 1 is not that dramatic inside the VM. So even like if we have like a reasonable slowdown, it is okay.
Okay, final question. Nami asks, but does GKR have other security issues?
Yes, but yes, in some sense, yes, it's a fair point. But I guess we can. I think there are some tricks. I know the paper that you think of. That you can use some tricks to avoid this kind of issue, but definitely, yes, it's a bit tricky. Yes, I agree.
Amazing. Congratulations to the 57 people who made it to the end of this 2.5-hour call. Potentially, I'll see a bunch of you on the next call where we'll talk about alternatives to Poseidon. Thank you so much to everyone and to the speakers. Have a great day. Bye.
Thank you.
Thanks.
Thank you.
Bye.